Okay, so I'm going to go over the notes that go along with the simulation you did yesterday. So in the atom, there's 3 particles that you've all heard about in middle school: protons, neutrons, and electrons. You need to know their charge, their location, and their size from there. So protons are positive. They're in the nucleus, the center of the atom. Their mass number is going to be 1 because they're larger, so they are included in the mass number. For neutrons, they are neutral. They're also in the nucleus, and they're also larger, so they are included in the mass number. For electrons, they're negative. They're outside the nucleus. They're in the clouds of the orbitals. They are not included in the atomic mass, so we give them a mass number of 0, so they're smaller. They're almost 2,000 times smaller, about 1/1800th of the size of the other two. So we went over how to use some different numbers. So there's a little key on the periodic table you see there. You'll see the same one on your same paper, so you want to make sure to pick up the periodic table from the makeup work trays. So mass number is always a whole number. You get it from the sum of the protons and the neutrons from it, or if you don't have that option, you're going to round the atomic mass to the whole number. So there's more than one possible mass number of an element, but the one that it's closest to in the periodic table is the most common. But if they give you protons and neutrons, you want to use that combination, so just ignore the decimal number. So for example, in this picture, you see there's 6 neutrons and there's 6 protons. You add those up and it's 12. So that's why we would call this carbon 12, because the nucleus contains 12 particles. So the whole number in the box is kind of the most useful thing on the periodic table. It's the way the periodic table is arranged. It tells you the number of protons of an atom in each element. It identifies the element because it's unique. I can change the neutrons, I can change the electrons, and something can be carbon. But in order to be carbon, it has to have an atomic number of 6 and 6 protons. Otherwise, it's no longer carbon. It's what we use to define everything. So again, the protons are the atomic number. The decimal number they get, the one with the decimals after it, is the average atomic mass. The label is AMU, atomic mass units, so we're very creative there. And it's a weighted average. So they take all the percents of each element on there, which is going to build up to the next lab we're going to do, and they figure out a number on that accounts for all the different known samples of each one. So again, if the mass number of protons or neutrons is not given, then you're going to round the atomic mass to a whole number. But if they give you the name in the hyphen, like carbon 13 or carbon 14, that is your mass number. Ignore the decimal number in the table. So your neutrons, you're going to get those by subtracting some mass number minus atomic number. So for example, in phosphorus 32, 32 is the mass number. You can look up phosphorus, its atomic number is 15. Take 32 minus 15 and it has 17 neutrons. So just think of this like if I told you I was grilling and I made 25 sandwiches and I told you 15 were hot dogs, then you could say 25 minus 15, she must have had 10 hamburgers. In a neutral atom, the electrons are equal to the protons. So if you're asked to find electrons, you always start out with the same number of protons, but then you adjust it if they tell you there's a charge. If you have a positive ion, there are less of the electrons and protons, where if you have a negative ion, there's more. So you just add up the pluses or minuses. So the charge is the difference between the two in there. You just add them up. So more protons would be positive and more electrons would be negative. So here are some examples: 15 protons, 15 electrons. That would be normal phosphorus. The overall charge would be 0. But say here that one of the electrons was given away. That would give it a positive charge. Say we gained 3 electrons. We now have 18 electrons. My charge would be 3 minus, or people might say negative 3. So what you need to be able to do is find all of these substances, or all these amounts given a periodic table. So you should know the atomic mass, the atomic number, the mass number, protons, neutrons, electrons. Charge you're going to assume is 0 unless they tell you otherwise, or if you see the number of protons and electrons. So go ahead and try this next part. Look up boron on the periodic table. It is in the second row. And you're going to, for it, find its information. So boron's over here, and then copper here is down in the middle with it. So on your periodic table, I want you to see where I got these numbers. So the first thing is you find the whole number in the box. So boron is 5 and copper is 29. Boron, you were not given a mass number, so you're going to round its mass to the nearest whole number on the table. So 10.81 rounds to 11. Copper 65. Now you'll notice this is not the mass in the periodic table, the decimal number. This is a different isotope of it. So the mass number is 65. Neither of these had a charge mentioned, so it's going to be 0. Your atomic number and your protons are going to be the same. So boron has 5 and copper is 29. Your electrons, unless you're told differently, are also going to be the same. So notice I put 5 and 29 in the electron column. But what we do need to figure out is the neutrons. So we know the protons and neutrons together equal the mass number. So for boron, it's 11. Subtract away 5 protons, or the atomic number of 5. Your neutrons is 6. For copper 65, we're going to take 65 minus 29, either 29 protons or atomic number 29. They're the same thing. And it would be 36. For ions, normally the protons and the electrons are equal, so they add up to 0 on the charge. But ions are elements that have gained or lost electrons. So if you haven't already, you need to do the balloon and the sweater activity. It is a PhET simulation. So what we saw is originally the balloon and the sweater had the same number of particles on here. But then we saw when the balloon came over, so originally it had 4 of each. It started picking up the negative electrons on here, and then the sweater originally had the same number of positives and negatives. But as those balloons picked some of those up, we didn't have as many more negatives. So the sweater lost, so it became positive because the negatives took away, and the balloon gained was negative because it picked up electrons. So again, ions, a negative ion gain electrons, it's negative. So you want to think of that as like Cl minus is chlorine with an extra electron. So let's look at that one. Chlorine normally has 17, that's its atomic number. But we're going to see that minus sign and think I need to add an electron. It's got another electron there, so it would have 18. Ca2 plus, find calcium on the table, it's 20. But it loses 2 electrons, so take away 2, and it has 18. Notice they both have 18. That is the number of a noble gas atomic number. So you'll see most of these are going to end up with a number that would be the same as a noble gas. So when I see a number like this is called the isotope notation. The top number here is the mass number. The bottom is the atomic. And then if there's a charge, it's going to be listed up here. If there's not a charge, you're going to assume everything's equal. So normally carbon would have 6 electrons. You get that from the atomic number. But 4 plus, remember, it's the opposite of the sign. So think about if you lose your negativity, you've got a more positive attitude. That's how this works. So 6 minus 4 would give you 2. So this ion would have 2 electrons because it lost 4. Let's look at some that do have a charge. So in both of these for charge, I put plus 1. So they gave you the top number, which is the mass number. So they didn't list the bottom number, but lithium always has an atomic number of 3, so we could put a 3 down there. So the atomic number is 3 for both. The mass for the first is 7, the second one is 6. That would not affect the protons, are both 3. Neutrons we're going to subtract like usual. So you can see it's kind of set up like a little subtraction problem here. If I, on here, would just take 7 minus 3 or 6 minus 3, that's how I'm going to get the neutrons. So just look at those two numbers with it. The electrons normally you'd have 3, but since it has a plus charge on there, it lost 1, so it has 2 for it. So again, if I have 3 positives and 2 negatives on there, that's how I end up with a 1 positive charge for that. So again, isotopes have the same element with different masses. They have the same number of protons, but different number of neutrons. So when we name it, you've got to say the name, the mass number, carbon 12, so people know which one you're talking about with it. However, when you're matching up the symbol, you will need to pair up these. So if I just told you what's the symbol for 12 over 6, you'd look up element 6 and it'd be carbon. And this just summarizes the difference between the two. They have the same protons, they have the same electrons, but they have different neutrons. Again, you could have something with the charge as well, but this is just normal carbon on here. So just carbon 12 has 6 because 12 minus 6 gives you 6. And then carbon 14, 14 minus 6 gives you the 8 neutrons.